But when they grow, basically these catalysts like iron, carbon is somewhat soluble in these catalysts. Okay, so at these temperatures, around 900 degrees, is when you break down your carbon source, like methane in this case. And methane starts cracking. I think it cracks at like 980 or 950. So usually you run between 890 and 950 here. So you start to crack the methane, you get some free carbon. The carbon precipitates onto this iron preferentially. And these iron nanoparticles, you have to use nanoparticles, right? So these iron particles are of the order of few nanometers. And the carbon forms on either side and starts growing as a tube. So it grows as a tube on the iron.
So does that shape then determine the shape of the nanotube? Like can the size of the nanoparticles determine the size of the nanotube?
I've not been able to determine. It does to some extent. It does to some extent, yes. It does to some extent, but not fully, because usually these nanoparticles are actually quite a bit bigger than the tube. So the tube is typically smaller than these. So yes, that's one of the things people have made bigger nanoparticles and grown bigger tubes, or smaller ones and grown smaller tubes. There's a minimum diameter of the tubes because at some point you get bending energy. So, it must be, it's probably 10, where's the nanotube picture? At some point you bend, you can't bend it enough that you actually form a defect, right? So it's probably, 0.8 nanometers or something is the minimum diameter of it. And like I said, the particles are usually bigger than that. So they don't fully set the size of it, but they do, sort of wet, and they probably, depending on, something about the temperature and the energy of the bonding, right? They just form and grow as tubes. It's hard to know. For a while, there's a huge controversy for years as to whether the catalyst stayed where it was and the tubes grew above it, or whether it grew underneath. And now people think that, the catalyst stays at the top and it just continuously grows there. It's just actually, people didn't know this for a long time. So, it's still somewhat of an unknown process and not entirely, but yeah, so. But yeah, if you could grow graphene in an oven like this, you'd have 1 billion papers right now. It's not so easy to do. People don't usually grow it, so they exfoliate it from graphite. So you just buy graphite and Scotch tape and we put it on silicon. Silicon oxide. Actually, and so the other thing about graphene is that the real key to finding single layers was not just exfoliating it. Probably that's been done. But it turns out that when you look at it under a microscope and you have a 300 nanometer silicon oxide layer under the graphene, you can actually see a difference between 1 and 2 layers and more, right? So if you don't have that, it's just some interference effect. If you don't have that oxide layer, you just see lots and lots of pieces of stuff, and you'd have to do an AFM on all of them to see the thickness, and it's impossible. It's two times consuming too many things. But if you can actually optically see the graphene candidates, then you can actually find it and manipulate it. And that was the big difference there, which is sort of funny. But yeah, usually it's on oxide. You can only see it on these silicon oxide things. So